All right, so we've got an introduction to cryptography today. All right, so we can add security to messages. So we want to make sure that we can send messages securely. It's a very important issue in the information age when we send messages electronically all over the place. And we send really important information like credit card numbers, etc. Okay. So consider the number of times you send information that you hope is secure. Text messages, emails, online shopping. So it is largely impossible to prevent messages from being intercepted. You send them out into the internet, anybody can grab them. Okay? So once they're out there, you cannot control who gets their hands on it. But we can try to disguise them so that the messages only make sense to the recipient. Okay? So even if somebody gets it, they can't read it. So this process is called encryption. Disguising your message so that only certain people can read it. Okay, so whenever we encrypt a message, it's really important to do it systematically. Both you and the person you want to send the message to have to agree on a secret system, the way that you're going to disguise the message. And many systems are based on a keyword or a phrase that's only known to the sender and the recipient. So just a little vocabulary. Cryptography is the study of the processes by which information is disguised so that unintended recipients can't understand it. So that's the definition of cryptography. And a cipher is a reversible rule for disguising a message. Cipher, another more commonly used word for cipher is code. There are many, many, many different ciphers. We're just going to learn about a few in this little mini unit, different ciphers that are used. Okay, so encryption is the process of disguising the message. Decryption reverses the process. It takes a disguised message and turns it into something that makes sense. And we want our ciphers to be simple enough to use regularly. We don't want it to be ridiculously hard or time-consuming to disguise a message. But it needs to be complex enough so that the message can't be easily decrypted by someone who doesn't know the rule, right? Someone can't figure out what your rule is because it's too simple. Now, one really important thing is that your cipher has to be reversible. If you code your message to make sure that no one else can read it, you have to be able to decode it, right? Otherwise, what's the point? The information is just lost. So it has to be undisguised, undisguisable. All right, so one of the simplest ciphers and the first known uses of a cipher is the Caesar cipher, named after Julius Caesar, who used it to communicate with his generals. So the Caesar cipher takes the letters of your message and changes them according to this rule. Every letter of your message is going to be replaced by the letter that is 3 places later in the alphabet. So every letter gets replaced with the letter that's 3 letters after it. So A's become D's, B's become E's, C's become F's. Everything shifts 3 to the right. So what do you think happens when you get to the end of the alphabet? A, B, C. Yep. W becomes A, Y becomes B, Z becomes C. Just wrap it around. So if I want to use this code to encode the message attack at daybreak, I start by writing out my whole message, attack at daybreak, and then I take each letter and I go 3 to the right. So I go A, B, C, D. T, U, V, W, U, V, W. So C becomes D, E, F, right? So you just go 3 later. K becomes L, M, N. So K becomes N. Does this make sense? So every letter just becomes the letter 3 later. And we get this message that looks like junk, right? It makes no sense at all. That's the whole idea. We want to take a message, make it look like junk so that other people can't figure out what it says. We typically omit spaces and other punctuation when we encode messages. So you notice that I did that in this example. No spaces, no punctuation. That is because knowing the lengths of words or knowing where sentences end can give somebody trying to figure out your code can give them a clue to the contents of your message. Because one letter words have to either be A or I. And then now you know what one letter is. And you can guess everything else. However, to make the message more readable or nice looking, we often split it into blocks of equal length. So in this particular case, we can split it into blocks of length 4. So I just took my encoded message and made little 4-letter words. It's okay. All right, an example. All right, so if I want to decode the message, I have to undo what I did. Where have you heard that do, undo before? Like a do list and an undo list. That's an algebra, right? So this is related to algebra in that do, undo thing. To undo what we did to the message, you have to undo exactly the process that you did before. So our process to encode was move everything 3 to the right. So to decode, move everything back 3 to the left. So we need to go backwards 3 places in the alphabet. So if we were going to do that, let's just do the first 4, D, W, W, D. D, W, W, D. So 3 letters before D would be A. 3 letters before W would be T. Right? And I'm starting to get my message attack at daybreak back. All right, so here's a message that I encoded using the Caesar cipher. Looks like gobbledygook. I want to figure out what it says. So take a couple minutes and see if you can decode it. You got it. All work and no play makes Jack a dull boy. From The Shining. Okay, so the Caesar cipher is an example of what's a wider kind of cipher called a substitution cipher, where each letter of the alphabet is replaced by a different letter according to some consistent rule. Right, so the Caesar cipher, the consistent rule is 3 later in the alphabet. Replace each letter with the letter 3 later. The cryptoquote puzzle or cryptogram puzzle in the newspaper is an example of a substitution cipher. So one particular kind of substitution cipher is a shift cipher. And the Caesar cipher is an example of a shift cipher. Everything shifts 3 to the right. But there's nothing special about 3. That's just the number of letters that Caesar chose to use. You could use 4 or 5 or 13. So the rule for substituting letters involves shifting forwards or backwards in the alphabet. So one commonly well-known shift cipher is the rot 13 cipher, which shifts 13 places forward in the alphabet. So breaking substitution ciphers, they have a really big weakness. They're pretty easy to break because the rule for substituting letters is always the same throughout the entire message. And it makes this relatively easy to break, especially if the message is long. Because one thing about the English language and most other languages is that some letters are used more often than others. Right? So the most common letters in English are A, E, and T. This is a table where each letter of the alphabet is ranked in how often it's used. Okay, so as you can see, E is by far the most frequent letter used in the English language. And then we've got T and A as the other two most frequent. So what you can do is you can look at the encoded message, find what letter in the encoded message is being used the most frequently, and guess, say that's probably T, right? And then from there, you might be able to figure out a little bit more. So it is definitely a guessing game, but you have sort of an educated way to do the guessing, and it helps you crack the code. So I gave you one of your homework problems is like a cryptic quote from the newspaper where you do this. We'll see. All right, so the main problem with the substitution ciphers is that the order of the letters doesn't change. And so this is called frequency analysis, by the way, when you use the frequency of the letters to try to break the code. Frequency analysis. So substitution ciphers are really vulnerable to frequency analysis. So we can try to develop more advanced ciphers that try to avoid this problem. So here's a new method. This is called the bifid cipher. It uses a device called a Polybius square, just a 5 by 5 square, and you fill the alphabet in the grid. But there are only 25 spaces, so I'm just not going to put J in, because J is not a very frequently used letter. And if J happens to be in my message, I'll just replace it with an I. And whoever is receiving this message will figure out what the message is supposed to say. So I'm just going to write in my alphabet, A, B, C, D, E, F, G, H, I. I'm going to leave out J because I only have 25 spots. So I got to throw away one letter. So I go to K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. All right, so I have my Polybius square. All my letters of the alphabet, except for J, have a spot in it. So we can put the alphabet in order like that, or we could start with a keyword. We can start by filling in the letters of the keyword, and then the alphabet, any remaining letters from the alphabet afterwards. So let's say my keyword is confidential. I start by writing out confidential. I've already used an N, so I can't write N twice because I only have 25 boxes. So I skip the N and I go to the T. I've already used I, skip that, and I go A, L. So I write out the word confidential, but I leave out any duplicates. Right? You can only put each letter in a box once. So everybody see what I did? You can't repeat a letter. Can't repeat a letter. So I'm writing out confidential, but once I got to the second N, I skipped it. Right? I can only put each letter in once. Can't repeat a letter. All right, so now that I've written out my keyword, leaving out any duplicate letters, now I write in the rest of the alphabet in order, any letters that I haven't already used. So I've already put in an A, so my next letter will be B. I've already put in C, D, and E. So the letter that comes next is F, then G. Oh, because I already have an F, D, E, and F. I already used F. So I go to G, H. I already have an I. I never put J in my Polybius square, so I go to K. I already have L, M. I already have an N and an O, so I go to P, Q, R, S. I already have T, so I go to U, V, W, X, Y, Z. It's really easy to make a mistake in this part, but it's also really easy to tell if you've made a mistake, right? If you have extra letters, you're like, you know, the last letter you put in the lower right corner was an X, you know you've repeated some letters, right? And if you get your Z, if you write a Z here, you know you've left some letters out. So you can always figure out whether you've made a mistake. And then you can go back and try to find where the mistake was. No duplications ever. Yep. Each letter goes in one box except for J. All right, so now we know how to make our Polybius square. I'm going to use it to encode a message. I already did this. Okay. So I'm going to encode the message retreat. So every letter in the Polybius square, I could express where it is in the square by giving the row and the column. So, but first, and you'll see why, we have to make sure our message has an even number of letters. Retreat only has 7 letters, so we're going to add a dummy character to the end like an X or a Q, some letter that's not easily confused with the original message. So I write out retreat X. All right, so now each letter has an address in the Polybius square, a row and a column. So we look up the letter and write down its row and its column. So R is in row 4, column 3. So here's my R. It's in row 4. So these are my rows. These are my columns. All right, and then E is in row 2, column 2. And T is in row 2, column 3. R, 4, 3, 2, 2. A is in row 2, column 4. T, I already looked that up, that's 2, 3. And then X is 5, 3. All right, so once I've encoded each letter as a pair of numbers, 4, 2, 2, 2, 2, 3, each letter has been encoded to its address in the Polybius square. The next step is to take this list of numbers and instead of writing it vertically, write one long horizontal line. So take the list of numbers that's on the bottom and move it up next to the list of numbers that's on the top. I already did this. So next, we group them in pairs, reading from left to right. And you get this. So we had them vertically, 4, 3, 2, 2. Just take all these numbers on the bottom and write them out across left to right. 3, 2. That make sense? Take the numbers in the bottom, write them out left to right. Then you read them in pairs from left to right. So I'm going to read 4, 2, 2, 4, 2, 2. This is why your message has to have an even number of letters, so that when you do this circling of 2 when you go left to right, you'll have an even number of pairs. So you end up with something that looks like this. Group them in pairs, reading from left to right. Then you look up each of these pairs in the Polybius square to get a new letter. So 4, 2, we look up row column, and now that's a Q. 2, 4 is an A. 2, 2 is E. 2, 5 is L. 3, 2 is G. 3, 3 is H. 2, 4 is A. And 3, 3 is H. So we've changed our message into garbage, which was the idea, right? Whoever what? Oh, whoops. I made it. Okay, so there's a typo in your notes. Make sure you fix it. In the notes, it says that 2.5 would get encoded to W, but it's really an L. This W should be an L. I looked it up backwards, which is an easy mistake to make. You got to remember row, column, row, column. Yes, undoing this is much more difficult than undoing Caesar. Yeah. So there's our encoded message. This should be an L. To decode, simply reverse the process. Simply, right? Look up each letter in the Polybius square, write down the row and the column, but write them left to right. Okay, so we're going to undo what we did. So we have to take the steps that we did to encode and do them backwards. So the very last thing we did was look up these numbers and get letters. So we're going to take each of these letters, look up the row column, and write them left to right. Nope, left to right. Yep. So we're going to write them down left to right. Then you split the message in half, put the second half below the first half, and read the letters vertically. Okay, so here's a message that was encoded using bifid in a Polybius square based on the keyword Schwarzenegger. So I want to decode it. Okay. So first I have to make sure that this message has an even number of letters, which it does, 16. Then create a Polybius square. So I start putting in Schwarzenegger, but I can't repeat any letters. Okay, so I start writing out Schwarzenegger, but I leave out an E and another G. Some other letters get left out, and then you put in the rest of the alphabet. Okay, so I write down each letter of my message, my encoded message, which was SAWABT, blah, blah, blah. You look up each letter and write down its row column left to right all the way across in one line. Because this was the last step of how you encode, so it's the first step of how you decode, right? To undo, you do things backwards. Okay, so think about, if I put on my socks and shoes, to undo it, I have to take off my shoes and then my socks, right? So when I undo what I did, I have to do it in the reverse order. So I look up S, and I get 1, 1. So I write 1, 1, left to right. Look up A, that's in row 1, column 5. So I write 1, 5 next to each other, left to right. W is 1, 4, etc. I look up every letter, just write down the row column left to right. Then find the middle of the message. So let's see, I have 16 letters, so 1, 2, 3, 4, 8. This is going to be the middle of my message. I'm going to take the right half, write it underneath the left half. That undoes the step I did where I took the bottom and wrote it next to it. So I write this underneath, and I'm going to have 3, 5, 1, 1, 5 1, 5 3, 4 1, 1 5, 1 5, 1 5. Then read the numbers vertically, 1 3, as a row column, and get the letter from the Polybius square. So 1 3 is H. Oh yes, the next letter is A. Yeah. And then 1 5 is A. Yep. So I'm reading them vertically now. 1 and 3 go together. 1 and 5. 1 1 5 1. So I think I have it written a little nicer. Break it in half. Put one underneath the other. Now I'm reading them vertically. Okay, good. So 1 3 H, 1 5 is A, 1 1 is S, 5 1 is T, 1 5 is A, 4 1 is L, 1 5 is A, 5 3 is V, 3 4 is I, 1 1 is S, 5 1 is T, 3 1 is B, A, B, Y. Hasta la vista, baby. Yeah. If you were meant to be someone who's decoding it, you would have to have the keyword. Yeah. If you were not the intended recipient and you were trying to break this code, it would be really difficult because every letter doesn't get encoded as the same letter, right? So my original message, hold on. My original message, I'll rewrite it. Nope, I don't have it in mine. So hasta la vista, baby. The original message was SAW, right? Okay. So when I encoded it, A gets encoded sometimes as A, sometimes as S, sometimes as V, right? So A doesn't always get encoded as the same letter. So that makes this much more difficult to break than the substitution cipher. Does that make sense? Okay. Caesar is an example of a substitution cipher, where the substitution rule is substitute each letter with 3 to the right. But we could make up a million different substitution rules. We could say 5 to the right or 2 to the left or 32. Yeah, sure. 13. 13. Yep. Yep. Okay, so your homework is the Intro to Cryptography worksheet that shows up next in your packet. And I'm going to have you do it now as classwork, and then you won't have any homework. There's no homework in my math lab. The only homework for these last 3 classes is your worksheets. As you may have noticed on the last test, I like to put homework questions from worksheet homeworks on the tests, because since it's not in my math lab, I can't tell if you did it. So I put it on the test to make sure that you did it. Okay. So these are, do them, but I won't collect them, but there may be a question from them on the test.